Hello, everyone. It's now time for the third and final portion of the Chapter 10 notes. We'll be discussing the concept of angular momentum and the conservation thereof. I refer you to page 17 of your note packet. All right, so angular momentum, you can kind of think of as a tendency for something that's spinning to keep spinning and for something that is stationary to not spin. Similar to torque, angular momentum is defined as, the letter L, or it's represented by the letter L, and it's equal to the position vector crossed with the linear momentum vector. So that's R cross P is L, the L vector, which is also equivalent to the mass of the object times r crossed with the velocity vector. So m times r cross v is the angular momentum. Similarly, and similar to torque, you can also think of this with the cross product as it being defined as the mass times the magnitude of the position vector times the magnitude of the velocity vector times sine of theta, where theta is the angle between the position vector and the velocity vector. And remember that mass is a scalar, so we can use it in either of these two contexts just sort of by itself. There's no magnitude to it, it's a scalar. Also, similarly to torque, you can define the angular momentum as being equal to the position vector, or the radius, times the perpendicular portion of the momentum. So again, if you have something which is perfectly perpendicular, then you multiply it directly. And if you're dealing with a vector that has a component which is perpendicular to the r vector, then you're just looking at the perpendicular component as being contributing to the angular momentum. And so you can say that the angular momentum is equal to RMVP, where P is the perpendicular portion or the perpendicular component of the velocity vector. And contrarily, you could also say that it is the perpendicular portion of the position vector times mv. So the portion of the position vector which is perpendicular to the velocity vector. All right, so in this diagram here, we find that the angular momentum is equal to the moment of inertia times the angular velocity, or I times omega. And the units of angular momentum are, so we know that the I, the moment of inertia, is in kilograms times meters squared. And omega, which is the angular velocity, is in inverse seconds, or seconds to the -1. So L is going to be in the product of these two units, which is kilograms times meters squared over seconds. Okay, so let's take a look at a sample problem. So at the instant of the diagram below, we have a 8.060 kilogram particle P with a position vector r of magnitude 7 meters and an angle of theta1 of 46.0 degrees and a velocity vector v of magnitude 9.10 meters per second and angle theta2 of 31.0 degrees. Force F of magnitude 1.10 newtons and angle theta2, theta 3 of 27.0 degrees acts on particle P. All three vectors lie in the xy plane. About the origin, what are the magnitude of the angular momentum of the particle and the torque acting on the particle? Okay, so first thing to note is that L is equal to R cross P. So that's equal to the magnitude of the angular velocity, the magnitude of the angular momentum, L, is equal to m times magnitude of r times magnitude of v. So here's the r vector. Magnitude of v is going to be over here. And sine theta, the theta in this case, is going to be this angle, theta2, here. So if what you do is you plug in the velocity vector magnitude, which is 9.10, so you can plug that in here. You have the vector r of magnitude 7.0, and you can plug that in here. and you have theta 2, which is this angle here. If you plug that in for this, all you have to do is substitute, plug, and chug, and you will find that the magnitude of the angular momentum is 282 kilograms times meters squared over seconds. If we're looking at the torque, however, that is the r vector crossed with the force. So that's r cross f. And the magnitude of the torque is going to equal the magnitude of the position times the magnitude of the force times sine of theta. So in this case, we're looking at, I'll go ahead and erase all of my drawings here. We have this vector r here, we have this force vector here, and the angle between them is actually going to be theta 3. So what we can do is, once again, we have the vector r magnitude of 7.0, and we can plug that in here. We have the magnitude of the force, so 1.010 newtons, and that's here. And then you have sine of theta, and theta in this case is theta 3, or 27 degrees. Okay? So once again, when you plug all of that in and evaluate, you'll find that the magnitude of the torque is 3.50 newtons times meters. So note again that torque and angular momentum are somewhat related concepts in that you are taking a cross product, but you need to remember what cross product you're in fact taking. So just keep that in mind when you're looking at this example and for the rest of your life. Okay. What about a case where we actually have two separate particles? One thing which is kind of neat about the concept of angular momentum is that you can actually sum them. You can sum angular momenta together and thereby treat a system as a series of individual particles. So in the instant of below diagram, we have two particles moving in an xy plane. Particle P1 has a mass of 2.71 kilograms and a speed of 7.35 meters per second, and it's at a distance of 6.10 meters from point O, and we're going to call point O the origin. And particle P2 has a mass of 2.77 kilograms and a speed V2 of 7.89 meters per second, and it's at distance 6.97 meters from point O. So what's the magnitude of the net angular momentum of the two particles about O? So both of these particles are rotating about O, and basically because we're capturing them at just one point in their motion, that velocity is tangential. And as we've seen, when you have circular motion in general, that you have the velocity at a given point is going to be tangential to the point about which it rotates. So if we say, all right, how do we deal with what's the total angular momentum or the net angular momentum of this? That's going to be the sum of the individual angular momenta, that being L sub 1 for particle 1 and L sub 2 being for particle 2. And the question is, why did we pick the signs that we did? Why is this negative and this one positive? Well, if this is moving to the right, it's going to eventually, if it's moving in a circle, be moving clockwise, which is the negative direction by convention. And then this guy is going to be moving counterclockwise, and counterclockwise is the positive direction, again, by convention. So the total angular momentum is going to be negative L sub 1 plus L sub 2. All right. So the angular momentum is given by, or these individual angular momenta is given by the radius from the center, or from the point about which it rotates, times the mass times the velocity. So the momentum in this case is equal to negative d sub 1 m sub 1 v sub 1 plus d sub 2 m sub 2 v sub 2. And that's just, making the appropriate substitutions here and here. All right. So all we have to do is plug and chug. And once we have plugged in mass 1, distance 1, and velocity 1, and then distance 2, mass 2, velocity 2, if we take the magnitude of those factors, we end up with 30.8 kilograms times meters squared over seconds as the angular momentum of these two particles, or the combined angular momentum of these two particles. Okay. Just Newton's second law in angular form. This is kind of another way of kind of looking at Newton's second law in particular, that the vector sum of all of the torques acting on a particle is equal to the time rate of change of the angular momentum of that particle. So in kind of mathematics speak, the net torque is equal to the moment of inertia times the angular acceleration, but it is also equal to dl over dt. So that's the derivative of the angular momentum function with respect to time. So keep that in mind. That's a very handy equation, right? So the sort of proof of this, or actually another way that you can look at angular momentum, or you can interrelate angular momentum to other quantities that we've seen, is that for linear momentum, what we have is that linear momentum is equal to m times v. But if you have a rigid body and a fixed axis, you actually can take the direct analog, where the angular momentum is equal to the moment of inertia. Remember, moment of inertia is used in the place of mass in a lot of these equations. And then you have the angular velocity, and the angular velocity is kind of the analog to linear velocity for linear momentum. So there's kind of a big, long proof here. I sort of don't want to go into it, but you know, basically trust me that this relation does in fact hold. You know, and again, if you want to work your way through the proof, here is the proof. So go ahead and knock yourself out. There are other kind of corresponding variables and relations for translational and rotational motion. So in the linear world, we have F equals ma, and as we've seen again and again, in the rotational world, the net torque is equal to the moment of inertia times the angular acceleration. Similarly with linear momentum, you can either write that as momentum equals mv, or momentum equals mv times the center of mass. And the angular momentum can be written either as r cross mv, or moment of inertia times omega. Again, this is where you have, if you have a series of points, so if you have a set of points, set O points, and this second relation is more useful if you have an object. If you've got one kind of solid object, and you've got your moment of inertia already handy and calculated. Newton's second law, once again, F net. F net being dp, that should be a p, so this is dp by dt. And by analogy in the rotational world, net torque is equal to dl dt, right? And conservation of momentum, momentum initial equals momentum final, and angular momentum initial equals angular momentum final, again, assuming that you have an isolated system. So in the linear world, this is assuming that there is no external force, which is acting on your particles as they're colliding. And in angular acceleration, this is assuming that there is no exterior torque, that there is no basically push to rotate. Now, interestingly enough, when it comes to angular momentum, you could conceivably have a force which is acting on the particle or acting on whatever it is that is rotating, and you are not actually changing the angular momentum. How could that be? Well, if the force is acting parallel to the radius, it doesn't actually have a torque. You know, a torque requires an angle between the force and the radius of the object. So kind of a weird thought is that you can't have a net force and conserve linear momentum, but you could have a net force and conserve angular momentum, provided that that force is not actually causing any torque, or is not actually contributing any torque to the system. That's kind of a weird concept, but well, life is weird. Anyway, conservation of angular momentum. So where this comes into play is we've seen how the angular momentum is dependent on this quantity I, on the moment of inertia. However, moment of inertia is dependent upon the shape that something takes. We've seen how we have different moments of inertia for a sphere or a hoop or something like that. We've also seen how there are different moments of inertia depending on how far away from the center there is a mass, or how far away from the center of mass the mass is concentrated. So you can imagine a situation where by changing what I is, by changing what the moment of inertia is, you can change the angular velocity, because the angular momentum has to be conserved, assuming that there is no outside torque. So the example of this, the ballerina demonstration, which I will put a link for in the description of this video, is if I'm spinning, or somebody is spinning on a frictionless stool or something like that, and they're spinning very slowly, and they have a set of dumbbells out to the side. If they bring those dumbbells in closer to their body, they will begin spinning much more quickly. And I'll let Zach Tobin demonstrate that for you, again, with the link in the description. This is also, incidentally, how, if you've ever seen figure skating in the Olympics, where you have, somebody that comes out and they've spread their arms really wide, and then they tuck and they kind of put their hands over their head and they begin spinning very, very quickly. And this is physics in action. By changing by changing the shape of the object that is rotating, you are able to change how fast it is rotating, even without some sort of outside force or outside torque. So that's kind of a cool and sort of wild idea. And again, seeing is believing. So you should definitely check out the demo that I'm going to put a link to in the description. Okay, so here's a sample problem, and here's an example of sort of this kind of concept in action. A gymnast can reduce her moment of inertia by a factor of 3 when changing from the straight position to the tuck position. Her initial moment of inertia is exactly 3 times her final moment of inertia. If she makes 2 revolutions when in the tuck, in 0.90 seconds when in the tuck position, her angular speed when in the straight position is closest to what? So we're given her speed, her angular velocity in this tuck position, and we're asked what the angular velocity is in the straight position. Okay, so let's go ahead and do that. We have to remember that angular momentum is equal to the moment of inertia times omega, times the angular velocity. We also need to remember that the initial angular momentum and the final angular momentum are going to be the same. There is no torque. There is no external force which is acting on this particular gymnast at this time. So what can we say? We can say that the initial angular momentum is given by the position in the straight when the person's straight up and down, and omega in straight, and that's also going to be equal to 1/3 of I straight times omega in the tuck. Why is that? Because we know that the the moment of inertia in the tucked position is 1/3 the moment of inertia in the straight position. So that's why we put this 1/3 here, and we don't have to introduce an additional variable. Okay, and because we don't have to introduce an additional variable, we can cancel out the variable that we've got. Okay, and also why am I saying that L initial equals this kind of final straight position? That's because L initial equals L final. It doesn't matter what I put here, whether that's L naught or LF. Okay, so we've canceled this out, and we now know that omega in the straight position is equal to 1/3 omega in the tuck position, right? So then we have to say, all right, what's omega in the tuck position? We're given that it is 2 revolutions in 0.90 seconds. So how much is that in radians? Okay, so once again, dimensional analysis, 2 revolutions over 0.90 seconds. We convert revolutions to radians. We go ahead and make this division, and we find that omega in the tuck position is 13.96 radians per second, right? So because omega in the, actually, sorry, there's a bit of an issue here with the labeling. Okay, so we know that that is omega tuck. We plug that in here. And then what we find is omega straight. Right? So we find omega straight. We just divide this by 3. It's 4.65 radians per second, or 0.74 revolutions per second. And our answer is A. All right. Let's have a look at another problem. In the figure here, there are 3 particles, each of mass 0.026 kilograms, fastened to 3 rods of length d equals 0.15 meters, and the connectors have negligible mass. So we don't have to worry about that if we're doing something like a moment of inertia calculation, that kind of thing. The rigid assembly rotates about point O at an angular speed of omega equals 0.55 radians per second. About O, what's the first rotational inertia of the assembly? That's also known as the moment of inertia, sometimes referred to as the rotational inertia. B, the magnitude of the angular momentum of the middle particle. And C, the magnitude of the angular momentum of the entire assembly. So for the first one, to find the moment of inertia, and this is kind of a review here, a light review, that's equal to the sum of MI/RI squared for each of these individual particles. So there are going to be 3 of them. We've got 3 terms. So this would be from I equals 1 to 3. Okay. So what does that mean? That's going to be I equals MD squared. Okay, so that is this first, out to this first point. Okay, that's the first term. The second term is going to be M times 2D squared. So we're looking at this point here, and that's M2 R2. Right? And that's going to have a distance of 2d, so m times 2d squared. And then by analogy, third mass is going to have a distance of 3d, so m times 3d squared. We go ahead and evaluate this, and we find that the total moment of inertia, or the total rotational inertia of the assembly, is 14 md squared. Okay, and we know the mass, we know the d. We can actually find this numerically, but I'm just going to leave it like this. Okay, so for point B, we're looking at the angular momentum of just the middle particle, and that's going to be equal to the moment of inertia of just that middle particle times the angular velocity. So if we're looking at just the angular angular momentum of that second particle, that's the guy that's right here, then the distance is going to be like that, and we disregard the other two masses. All right? So the angular momentum is going to be L equals md squared, or sorry, it's going to equal 4md squared. The distance here is 2. So what we're looking at is m times 2d squared. We're looking at just this component because we're only concerned with that middle mass to find the angular momentum of just that middle mass. So angular momentum is equal to 4md squared times omega. And omega is going to be the same for each of these 3 points, each of these 3 masses. We go ahead and we can substitute in, and we find that the angular momentum is 1.29 times 10 to the negative 3rd kilograms times meters squared over seconds. Okay? But then when we are asked about finding the total angular momentum of the entire assembly, then what we have to do is use I total, the total moment of inertia, and which we've already calculated up here. Go ahead and plug that in. We also know what omega is, and we can find that L equals 4.50 times 10 to the negative 3rd kilograms times meters squared over seconds. Okay, so far so good. Let's have a look at another problem here. 2 discs are mounted on low friction bearings in the same axle and can be brought together so they couple and rotate as one unit. So basically what we have here, now you're going to see if my drawing skills are any good, is that we've got one wheel here and it's spinning, and we got one wheel here and it's spinning. And what we do is we bring these 2 wheels together so that what we end up with eventually is 2 wheels side by side spinning as a single assembly. All right, so if you can kind of think of my hands, these are wheels and they're spinning in this direction, and I bring them together and then they spin together in this direction. All right, so that's what this problem is asking us to do. We're given the rotational inertia of the first disk and of the second disk, as well as the speed and the direction in which they are spinning. Okay, so this is actually analogous to example 10.11 in the book. And you can actually treat it as an inelastic collision. You can treat it as an inelastic collision of 2 wheels. And remember that in inelastic collisions, momentum is conserved, and that goes, I don't want to say it goes double, it goes just as much for angular momentum as linear momentum. Okay, so in practical terms, what does this mean? It means that IA omega A plus IB omega B is equal to IA plus IB times omega, and omega being the final angular velocity of that combined assembly. So I've got IA omega A, I've got IB omega B, they come together, and we have a combined system. All right? So if we solve for omega, that's a simple rearrangement. We see that omega equals IA omega A plus IB omega B over IA plus IB. Okay, so for point number 1, we just plug and chug. We're asked for the angular speed after coupling, and we're told, and this is important to note, that the first disk has this rotational inertia of 1.15 kilograms times meters squared. And we're told that it's spinning in the positive direction, in the counterclockwise direction, at 143 revolutions per minute. Now, I didn't want to show how to get that into hertz. It's kind of tiresome, but just remember how you generally do that, how you convert that into radians per second rather than revolutions per minute. Okay, so that's what that business is here. Second disk, we have this rotational inertia, which corresponds to this rotational inertia down here. And then we have spinning counterclockwise at 702 revolutions per minute, which turns out to be 73.5 hertz. Note that the spin is also counterclockwise. So these are spinning in the same direction, they're spinning in the positive direction, and that's why this factor here is positive, or why this sign here is positive. So we simply plug and chug into this expression, and we find that omega final is 64.4 hertz. And you'll notice that this is actually an angular velocity that is somewhere between the two. And also when you're dealing with a perfectly inelastic collision like this, you are getting a loss of kinetic energy to things like heat. So that also applies when you're dealing with this kind of mating, where you've got two things and they're coming together. When they mate, when they meet up with each other, there's going to be a lot of friction and there's going to be loss in kinetic energy. And remember, once again, and I've said this a bunch of times, the amount of energy in the universe does remain the same, but in our system, which we're just concerned about those two rotating disks, the energy that is lost as friction is lost to that system. The total amount of energy in the universe is the same, but it's not the same amount of energy in the two rotating disks. Okay, so now we're asked in part B, what if you have the negative case, or the kind of opposite case, where the second disk is spinning clockwise at 702 revolutions per minute. So here, this is going to be minus 73.5 hertz, and that's because a revolution in the clockwise direction is, by convention, a negative rotation. So it's a negative speed. We go ahead and evaluate as before, and we find that it is negative 59.8 hertz is the angular velocity of the case in B, where we have this guy spinning this way, this guy spinning this way, and they meet. And eventually the entire assembly starts spinning this way. Okay? All right, so that's an example. Okay, and then let's say that we have a disk with rotational inertia of 7.00 kilograms times meter squared, rotates like a merry-go-round while undergoing a variable torque given by this function right here. At time t equals 1, its angular momentum is given here. What is the angular momentum at t equals 3.00 seconds? And what's the angular velocity at 3.00 seconds? Okay, so we know that the torque is equal to the derivative of the angular momentum with respect to time. So therefore, the angular momentum is going to be the integral of torque with respect to time. I mean, that makes sense, doesn't it? And we go ahead and we take this function and we evaluate the integral, and we find that it is 5.00 t plus t squared plus c. Don't forget that there is a constant term there. All right. And also we're told what this function is equal to at time t equals 1.00 seconds. So remember that you've got to solve for c, given information where the rest of this function is behaving at a time of 1 second. So to solve for c, we say L1 is equal to 5.00 plus 5.00 times 1. So, sorry, 5.00 times 1 plus 5.00 times 1 squared. And we know that this eventually winds up being, oh dear, there's actually an error here. 5.00 plus 5.000 plus c, that's going to end up equaling 5.00 because that's what's given. So in this case, C is going to equal -5. Or, oh dear, okay. Sorry, that was actually a mistake. I don't know where this additional factor of 5 came from. So this 5 shouldn't be here. Okay, so 5.00 times 1 plus 1 squared, which is 1 plus c, is equal to 5.00, because that's what we're told is the answer to that function here. All right, and then we solve for c, and we find that c is equal to -1. All right. So we now know that the function for the angular momentum is 5.00t plus t squared minus 1. Okay, so then we simply say, all right, what is it at 3? We then plug and chug. So 5 times 3 is 15, plus 3 squared is 9, minus 1. Okay, that's our constant. And so the angular momentum at time equals 3 is 23 kilograms times meters over seconds. Right? Now, all we've got to do is say the angular momentum is equal to the moment of inertia times the angular velocity. We're given what the rotational inertia is, right? So once again, all we have to do is plug and chug. 23 equals 7 times omega. And then we go ahead and solve for omega, and we find that it's 3.3 hertz. Okay? So that concludes the notes for chapter 10. Take a good look at it. It's kind of the same but different, if you will, in terms of conceptually how it's set out. Have a look again at the link I'm going to post in the description, and I will see you next time when we talk about chapter 11, which is the concept of equilibrium. Thank you, and see you next time.